Okay, so it's recording. Can again just one of you confirm if my screen is visible and I'm audible?
Yes, sir.
Okay. Thanks. Thank you so much. Okay, so welcome to the eighth live interactive TA session for the NPTEL course Applied Linear Algebra for Signal Processing, Data Analytics and Machine Learning. This is an NPTEL course taught by Professor Aditya Jagannatham from IIT Kanpur. As usual, a little bit about myself. So my name is Yashvanth, and I'm presently a Ph.D. research student at the Indian Institute of Science, Bangalore, and currently advised by Professor Chandramurthy at the Department of ECE. My research interests broadly lie in statistical signal processing and wireless communications, while I currently focus on designing algorithms for intelligent reflecting surfaces for 5G and beyond wireless communications. You can always write to me in this email address for whatever kind of queries you have related to the course, and also in particular about the TA live interactive TA sessions. You can always write about it to me, and you can find more about me in this particular web link. Okay, so the specific topics that we will be covering for today will be on optimal linear filtering based on the LMMSE estimators which professor had covered in the class. Okay, so specifically we are going to see something called Wiener filtering and some prediction problems in time series which we encounter in everyday life. Okay, so we begin today's class with the part one, which is basically to do with the summarization of the week 8's lectures. So the week 8's lectures started with LMMSE estimations in linear systems. Okay, so linear systems are those kind of systems where your output input relationship is modeled by as a linear equation, right? So y equal to hx plus n is a linear model. Why? Because y is the observation, appears as a linear function of the input x. So this is called a linear system of linear system. Okay. um, One example where you can find a real-time application of where you can find such a linear system is basically in MIMO communication systems. Okay, so in particular for this kind of a linear system, what is the LMMSE estimation? Okay, we know that LMMSE estimated. So basically, if I'm given a linear system y equal to hx plus n, I get to observe what y is. But given y, the goal is to estimate the x, the vector x, right? So among the class of all estimators that estimates x given an observation y, a special estimator is called the linear MMSE estimator, meaning that the estimator x hat is going to be a linear function of the observation. That's why it's called linear. And what is the design criterion to design such an estimator? Based on MMSE, that is minimum mean square error. And this choice of the linear transformation, the matrix C, is going to be dependent on the criterion MMSE. Okay, that's why it's called linear minimum mean square error. Okay, so where if you apply this MMSE criterion, the C matrix will turn out to be this particular matrix Rxy times Ryy inverse. Okay, where Rxy and Ryy are the cross correlation and the auto correlation matrices. Okay, so now you can simplify your Ryy and Rxy more, specifically when when your observation y is comes from a linear system. Okay, that is what I'm saying. Your actual vector to estimate is it appears linearly in your observation, and this linear MMSE will take a linear function of the observation. So it's something like a cascaded relationship. You have the actual vector x, you take a linear observation, you have the actual vector x, you take the linear observation y, and then again you take a linear estimate x hat. That's why it's called linear MMSE in linear systems. Okay, now, in particular for a linear system, you can simplify your Rxy and Ryy more considerably. Let's see how. So I just apply the definition of Ryy, namely that it is the expected value of y transpose. Right. So y is an, let's say, n by 1 vector. So y transpose is a 1 by n vector. So y transpose is a matrix. That's why it's called an autocorrelation matrix. Why autocorrelation? Because I'm taking r y y, I'm multiplying y twice out. This is also called the product, outer product. Okay, this is a product of the same vectors. But here, if you see Rx, Y, I multiply X with Y transpose, not X transpose. So this is called cross correlation. Okay, but this is called auto correlation because I'm taking auto, something like within itself. So what I do is I expand my Y as Hx plus N. That is the linear system. Okay, and similarly for Y transpose also, put Hx plus N the whole transpose. Now you simplify this, you will get something called equation 1. Okay, so we have, so where Rxx is the autocorrelation of the autocorrelation matrix of the vector X. See, okay, and similarly Rn is the autocorrelation of the noise, this n vector that you see here. The autocorrelation for this noise is given by Rnn as a matrix. Okay, so I have expressed the observation autocorrelation matrix as a function of the actual parameter autocorrelation matrix and the noise correlation matrix. And and this H and H transpose are the, basically H here is the linear, the matrix that comes in the linear system equation. Fine. So similarly, you can show that your Rxy, you can write it as expectation of X into Y transpose, where Y, I substitute the value for Y, it becomes Hx plus N, right? So this you can show that this will become Rxx times H transpose. Okay, so just use 1 and 2, gives a value for Ryy and Rxy. Use both these expressions in this equation A because Rxy and Ryy is what we want. And we have found out what are these values for a linear system. If you substitute for these inverses Ryy and Rxy, your linear MMSE estimator for a linear system is basically given by this expression. This basically is your Rxy. This basically is your Ryy. And this is an Ryy inverse. So there's a whole inverse times your observation Y. Okay. So this is basically your linear MMSE for linear systems. Okay. Now, in the context of MIMO communications, you can, whenever, so basically, if you consider this system to be something like a MIMO channel, okay, then what is X? X is really what we transmit. My multiple input, multiple output means you have a pair of communication transmitter and a receiver, where the transmitter wants to send some information data to the receiver. Okay, using multiple antennas. There are multiple antennas. Uh, am I okay? Just confirming. Am I audible?
Yes, sir.
Okay. Okay. Yeah. Thanks. So. Um, if you have a MIMO system, you have multiple antennas of the transmitter and multiple antennas of the receiver. At the transmitter, through the multiple antennas, I want to send some information data. And it will pass through the channel, air channel. And as a receiver, all the multiple antennas will capture the data, the received signal. From the received signal, I need to decode or estimate what was the transmitted signal by the other end, right? For example, if I'm talking through mobile phone to you, then over the channel, once your mobile phone receives my signal, it should now decode or estimate what I originally transmitted to you. So that is basically captured by this mathematical equation here. If I transmit X and I observe Y, basically after getting Y, the goal is to estimate your X. Okay, so that can be, so basically in that MIMO context, communication system context, X is something that is called a transmitted symbol. So the goal of any receiver is to decode or estimate the transmitted symbol by the transmitter. And in that kind of a system, you can show that if you apply the LMMSC based procedure to the estimator X, you can show that your is the estimate of the transmitted symbol, okay, can be simplified as this. Okay, where H transpose H basically the channel matrix, and 1 by SNR is basically the signal to noise ratio. I think we, now that we have seen the definition of signal to noise ratio quite a bit, okay, and Y is the received signal at the receiver. Okay, and uh, associated with every estimator, you will also have some error, because it's not that x hat is not always equal to x. The x hat minus x, the difference will be very, very small. But it's not always possible to get an x hat which is exactly equal to x all the time. Okay, because there are always noise associated with every kind of observation. Even the estimator could also not be very, very, good enough, efficient enough. So we always have to live with some estimation error also, right? So that's why this error, what is the best estimation error, is given by this REE. It is also called error covariance matrix or error correlation matrix for a zero mean noise. Okay, this is given by this particular expression. Okay, 1 by epsilon times H transpose H plus 1 by R times identity, the whole inverse, where R is a trace of your Rxx and epsilon is a trace of your Rn. In some sense, this okay. In some sense, this will represent the signal power, and this represents your noise power. Okay, fine. So this for the first lecture was on describing the LMMSE for a linear system. Okay. Now in the second lecture, an explicit connection was made in terms of applying LMMSE for a wireless communication system. The first problem was the channel estimation. Okay. So now let me describe the system. You have a transmitter. It has T antennas. Okay. 1, 2, and through on till teeth antenna. Okay. You have a receiver at some other point. And in between, there's an air channel. It's an air channel. Okay. So each of the link between the one of the transmitter and the receiver is given by its own channel mathematical channel coefficient. H1, H2, and so on till HT. Since there are T, links, different links, this channel is a vector channel because it just I only have T numbers, and it's a T cross 1 vector. Okay, but in the receiver I consider just one receiver antenna. That's why it's a T cross 1 vector. Had the receiver also had multiple uh, receiver antennas, then this channel would have been a matrix. It's called MIMO channel, NR cross NT matrix. But here NR is 1, so it's a 1 cross N vector channel. Okay. Now, if you see here, let me see this expression. If I want to estimate what was my received signal, that means it doesn't just suffice to know what your Y is. That is, Y is what you see at the receiver. You should also know your channel. H should also be known. Otherwise, you cannot compute this inverse quantity, right? So you cannot estimate what your X is. So in a variety of applications, one of the very important characteristic is to estimate the channel. In classical signal processing terms, this is also sometimes referred to as system identification problem. You need to first identify the characteristics of systems, and then you do some operations with the system. Okay, so in the context of communication, this is called channel estimation. Okay? You need to estimate your channel symbols. Okay, for estimating channel, what you do? You send some known pilot symbols. That is, this is also something we discussed earlier itself, right? The receiver will know what the transmitter is going to send. So really, it is not some hidden. I mean, it's the receiver will. It's not the receiver will not know what the transmitter is sending. So, for example, if transmitter sends X and receiver gets X dash equal to some H times X, okay, but receiver knows what this transmit symbol was. Just divide by X, you will get H, right? So essentially, this is also called channel estimation aided by pilot transmission, aided by pilot transmission. That is why I'm calling the word pilot, because the receiver knows what the transmitter is going to send. So these are something like pilots. They aid the estimation of channels. Okay, this type of systems are also called MISO, that is multiple input single output system, because you see there's only one antenna in the receiver, so it's a single output system. Okay. Now let's go on to see how to do the channel estimation procedure. Okay, so at a given time instant k, the received symbol is 1 cross 1 because there's only one receive antenna, right? So at the receive antenna, you will receive one particular scalar y of k at the kth time instant. What is it going to be? It is going to be Suppose the transmitter at the first transmitter sends x1. Sorry, first transmit antenna sends x1. Second transmit antenna sends x2. And the last sends xt. Then this will be h1 x1 plus h2 x2 plus h3 x3 and so on till ht xt. Correct? It's a linear combination of all these terms. If I write that in a vector product notation, that is exactly this. Okay, where k denotes at kth time. At every time I send different transmitted symbols, transmit symbol vector, which are known to the receiver. Okay, the receiver a priori knows at which at this particular at kth time instant what is the vector that the transmitter is going to send. Okay, the receiver will a priori know that. Okay, so that is called pilot transmission. So now, but this is your H vector, and these are your pilot symbols at the kth time instant. And you're also having some noise associated with this particular kth pilot transmission at the receiver. So what you do L pilot transmissions. L where denotes different. That means you take so at the first time instant send all the signals. You will get Y of 1. Then at time instant 2, send again another pilot transmission. Then you'll get Y of 2. Then like that, you keep on doing L times. Okay. If you keep on doing L times, you will get all the pilot transmissions. But with the constraint that every time you send from the transmitter, you send different vectors. X1, X of 1, X of 2, and so on till X of L. Okay. Where in turn, okay, basically this I called as X bar of K. Okay. This one basically this will be the received pilot transmission at the end of L time instances, L time transmissions. Collect all these y's. Each of this is scalar. So collect all these scalars and stack it as a vector y. Okay. Now this you can collect all each of these is a vector. X is a vector. Each of these is a vector, but different vectors. You can collect all of them and stack it in the matrix X. The H is constant across all. That is, I assume that the channel is not time varying. Okay, it stays constant for all the L pilot transmissions. So H is remaining the same. That will come here. And collect all the, okay, there's a small thing. So this is N1, N2, and so on to NN. So there'll be associated N noises. Collect all of them into vector. Okay, so this is of the form Y equal to XH plus N. Okay, so now what is this? I want to estimate H, that is my channel. I know all the received data, Y. So this is a linear system, right? This is similar to this, right? Very similar to this category, except that now H is like capital X, your small x is like small h. So for this kind of a model, apply the linear MMSE of the LMMSE of the channel estimation, right? So to do that, H hat LMMSE is given by CHY times CYY inverse times Y, where CHY is nothing but, say, I'm using the words RXY, I mean RHY, both are same, okay, C and R. Okay, where CYY is basically given by this particular quantity and CHY is given by this particular quantity. Substitute both of them in this particular H hat, you will get the final estimation, final estimate of your H hat. Further in the class, professor also simplified this particular expression and show that you can obtain the LMMC estimator at something like this. Okay, this is a very, very interesting expression which you should know. What this expression says is, okay, there's a small thing. There should be an inverse. Should be an inverse. Okay. So this particular expression says that when your SNR is very, very large, that is your signal to noise ratio at the receiver is very large. Okay, for example, 10 this to infinity. Then what is 1 by SNR?
0.
Yes. So it becomes 0. That is same as saying, then it basically this boils down to this expression, x Hermitian x the whole inverse x Hermitian y. If you remember, this is exactly the least square estimate of your vector h. It's exactly a least square estimate of vector h. So basically what this LMMSC does is, see, this estimate, this estimation is a good estimation only at high SNRs. At high SNRs, least square is good. But at low SNR, that is when the signal to power ratio, noise power ratio is very small, then least square estimator is a very bad estimator. But what happens with LMMSE is it will take care even in low SNR regimes by inverting. If the SNR is very low, it will make 1 by SNR and this quantity will become higher. Then basically this, if you can show that your LMMSE will perform even better than least squares at low SNR, and at high SNR, LMMSE will perform similar as a least square estimator. Okay, that is the key takeaway. What is the reason? Why is LMMSE performing at least as good as least squares? The reason is this least squares is just this much. But LMMSE, if you see the expression, it takes into account the statistics. That is, what is the correlation matrix? It basically exploits the correlation characteristics of the observation with that of the parameter which you want to estimate. But a least square will ignore that part. So basically, you're able, MMSE estimate is able to use that part, and it's becoming giving a better estimate. But it turns out that at high SNR, even without knowing the autocorrelation, I mean the correlation matrices, you can perform as good as the least square can still perform as good as LMMSE. So you just go with least square estimation. Okay, so that is what that is the main one of the main takeaway, in the sense, okay, when to use which estimator. Some estimator could be very complex, some other could be very simple, but that simple estimator may not be very robust, in the sense it can have a large number of estimation error. Similarly, the complex estimator could be very complex, but it may give you an accurate estimate of what you want to have today. But under some circumstances, it is possible that the result of the complex estimator could be same as your simple estimator. You need to identify those conditions, and whenever those conditions are satisfied, you can just go with the simplest estimator, and still the result will be same as what a complex estimator will give you. Okay, so this is the advantage of studying different estimators, and so on and so forth. Okay, and professor had also given in the class about the estimation error of an LMMSE estimator, different SNRs. See, at high SNR, the estimation error is given by this guy. At low SNR, estimation error is given by this guy. What is this? At high SNR, the means what, the signal to noise power ratio is very high. In that regime, the error is dominated by the noise variance. But at low SNR, it is dominated by the channel covariance. Okay, for now, just know this fact, because it requires more understanding of what is this channel covariance that is coming into picture. Okay, basically, we have introduced the LMC from a perspective of estimating the parameter x subject to minimizing the error, but there is little more to it. There is, in if you go to statisticians, and ask something about Bayesian methods of estimation, they will understand. In fact, MMSE is what is called a Bayesian estimator. Okay, so there is a very rich theory behind this particular statistical theory, but let's not go into that. Unless someone is interested, we can take it offline. But just know that there is something called the covariance of the channel itself. That is, h is what we want to estimate, and for every variable which we want to estimate, there is an associated covariance. Okay, just know this fact for now. We can discuss it maybe sometime else if someone is interested. The next interesting problem was time series prediction. Okay, this is something very realistic, in the sense that we all of us get to know. For example, if I want to tell the weather prediction in a given city over a month, let me quantify it by a number. Let's say temperature, for example. Today it can be at a given point in time. Let's say every day I want to measure the temperature at 12 p.m. in the afternoon. Then today probably it could be 20 degrees Celsius. Tomorrow it could be 22 degrees Celsius. The next day it could be 19 degrees Celsius, perhaps. It can keep on changing, right? That basically forms something called a time series. With respect to time, you keep getting new data set, new data points. So the data given is in that kind of a scenario, can you do some prediction? For example, based on today's weather temperature at 12 p.m. and yesterday's temperature at 12 p.m. Okay, can I predict what will be the temperature for tomorrow at 12 p.m.? That is like an example of prediction. And there's a lot of uses in prediction. For example, if I can tell some good prediction for tomorrow weather at 12 p.m., I can think about organizing some event at 12 p.m. Okay, now it's gonna rain. Let me not organize an event tomorrow. If it doesn't rain, okay, I will just go ahead and organize the event, and so on and so forth. There are a lot of utilities behind prediction problems. Okay, so you can cast this kind of a time series prediction problem as one of an estimation problem. Okay, meaning that given the data, okay, x of 0, x of 1, so on till x of n minus 1, you need to predict your x of n. That is the next data point. You have not yet seen x of n, but you want to predict what is the possibility that x of n can take. Okay? That is like an estimation problem. Use all these data, previous data samples, and estimate your next sample x of n. Okay, you can think about a prediction problem as an estimation problem. And in particular, if I want to do a linear estimation, I need to take a linear combination or a linear function of all these. It starts with 0 and ends at n minus 1, which means there are n data points. There are n data points here. Okay, so if I want to do a linear estimation or a linear prediction, I need to take a linear function of all these n data points, and I capture those linear function as these by these weights a1, a2, and so on till an. For example, if I just want to use L recent samples, okay, then that is something like this. This is called L step predictor because I use L steps. So, for example, x of x n minus 1, n minus 2, and so on till L minus L. There are L data points. Make use of L data points in order to predict the next sample. So, see, I have a hat here, means estimate the next sample. Okay? This is called a L step predictor. In fact, to be more precise, this is called a L step forward predictor. Why forward? Because generally, I have given all the previous data sample. I need to estimate what is x of n. But in some other problem, depending on the application, all my future samples are given. I need to estimate what is my previous sample x of 0. That is called a backward prediction problem. Okay, this is called a forward prediction problem. The future sample estimation of future sample is called forward prediction. Estimation of the most past sample or the oldest sample is called the backward prediction problem. Okay, you can cast both of them in under appropriate estimation problem and you can solve it. Let's confine to forward prediction in this class. Okay, now how to find these ANs, right? These are the linear coefficients. Again, the answer is use LMMSE principle. Okay, it is like the observations are xn minus 1, xn minus 2, and so on to xn minus L inputs. So these are the L recent observations are the inputs. The output, that is what you want to estimate, is x of n. Okay, then the LMSE estimation of all these a1, a2, and so on to al. Stack all these guys AIs as a vector. A equal to a1, a2, and so on till al. Okay, this I want to estimate this vector a. Again, very simple. Again, use a property. Your estimator of a is given by rxn of x times x bar times rxx whole inverse. Okay. Okay. So if you expand this rxx, you get something like this. And your rxn x is something like this. Okay. So rx of 0, rx of 1, basically it's a function. Rx is a function. Okay. Precisely, this is called the correlation function or autocorrelation function. If you remember what is correlation, what is the knowledge that I will gain by, let's say there are x1, x2, there are two variables x1, x2. If I know x1, okay, by knowing the knowledge of x1, can I tell anything about x2? Can I tell anything about x2? That is quantified by correlation function. Okay, auto, because it is with respect to same function, same variable x, but at different time instance x1, x2. Okay, So this is also called as what is called a Toeplitz matrix. In fact, Toeplitz matrix is very a very useful matrix in many variety of applications. But let's just move on with this. So we will in fact deal with this kind of matrices very in depth for today's class, and I'll explain more about how to construct Rxx, Rxn of x bar and so on in today's class. Okay, and you can show that the prediction error is given by something like this. Okay, and if you want to do a first order prediction, sorry, it's not a first order, it's a first step prediction, meaning that you just use the recent x0, only the recent sample in order to estimate your x of 1. That is, you don't have x of minus 1, x of minus 2, all these guys are not there with you. Just one sample, use one sample to predict the next sample. Okay, you can show that, use this expression. Okay, this guy, use this expression for this guy. You can show that it will boil down to this particular estimation. That is x hat of 1, that is the estimate of your data sample at x of the first time instant, t time t equal to 1, is given by rx of 1 divided by rx of 0 times x of 0. Okay, and the estimation error is given by this particular guy. Okay, you can always show that the second term is strictly a positive number and also strictly less than this number, which means this guy is strictly less than rx of 0. Okay, okay, so what does it mean? As you keep increasing rx of 1, as rx of 1 increases, then this error will keep on going down. What is exactly rx of 1? Rx of 1 tells the correlation between x of 0 and x of 1, right? Because they are separated by one time instant, 0 and 1. That's why you have 1 here. Okay, so it tells a correlation between x of 0 and x of 1. And by definition of correlation, if the correlation value is more, that is, if I can tell more about the other value, the value taken by other variable by knowing the knowledge of the first variable, then my estimation will keep on improving. That's why the error in estimation keeps going down as rx of 1 increases. Okay, that's what I've written it down here. And the last part of this week's lecture was an application into recommender systems. So basically, again, professor had given a very elaborate illustration of what recommender systems are. So recommender systems are those systems which are used to, for example, if you go to e-commerce websites and you want to buy something, okay, and the next time you go to the website, based on your purchase history and based on how other people have responded to this particular product's views, ratings, the website can recommend you with some other related object which you may be interested in buying. Okay, so that is called a recommender system. Okay, so this recommender system can be viewed as a matrix completion problem. That is, for example, if there are two products X and Y, and if there are two users, say 1 and 2, let's say user 1 have used product X and is given a rating on the website. Similarly, let's say user 2 has used the product Y and has given some other rating for that product on the website. Now, the matrix completion problem tries to predict or first it tries to predict the rating of how it would have been if user 1 had to buy the product, user 1 had to buy product Y, which he did not buy before. Similarly, this matrix completion will ensure to predict the rating for user 2 if he or she were to buy the product X, which he or she did not buy before. So this is called the matrix completion problem. And once you fill out the complete matrix, then you recommend, okay, depending on what is the highest predicted rating for a given user among all the products which he or she did not buy before, but you recommend the best, product which he or she can possibly buy to benefit more. Okay, so this can be attempted in as a two-stage solution. First, compute the sample average of all the ratings. That is, you would have gotten a list of all ratings for every user for every product. Okay, for all the products which these users have bought before. Okay, then determine something called the rating bias, because generally the ratings, let's say user 1 and 2 buy the same product X, the rating that they can give for these products can be very different, because user X may like something which user Y may not like, because every human being has his or own own likes and dislikes. Similarly, that is the bias across users. Similarly, there's going to be a bias across the products. The same product might not have a great utility compared to other product, because they are manufactured for their own purposes, right? They may not be comparable, so they will have their own biases. So that's why you need to do something. You need to determine something called the rating bias for every user movie pair. Then model every rating as a first order linear function of movie rating bias and user rating bias. Then you can, I think professor had solved in the class, you can post this rating modeling as a linear system of equations and solve for all the user biases and the movie biases. I think in particular, your professor had used movie as an example. So use movie for find the movie and the user biases, and finally predict the ratings for all the other left out entries in the matrix. That basically does the matrix completion of the complete user to movie rating problem. Then the recommender system will recommend the particular movie for a given user among all those unseen movies, the movie with the highest rating, predicted rating. Okay, so this was basically the recommender system, and with this the week 8 lectures were complete. Okay, so I see a question on chat. Why we assume X is linear? So, I'm sorry, I missed exactly which point. Can you tell me at which point are you asking this question? If it's okay, you can unmute and also talk. No problem. Okay, MIMO. X linear. Okay, so which part are you talking about? X linear. This part. X is a linear function of y, because I am interested in finding the LMMSE estimate of X. So it's a linear function of y. Okay, so I hope that answers. But channel is not linear. No, no. So basically, if I tell linear MMSE, what I mean by linear is your estimate should be a linear function of your observation. It doesn't. This is some matrix. I don't care. I do understand that there's an inverse operation going on, but that's okay. Everything can be abstracted by a matrix, let's say C. Your estimate should be a linear function of y. That is, y should appear as y. It should not appear something like sine of y or cos of y or y square. No, y should appear as y. Anything can multiply by. That is immaterial. So x hat is a linear function of y. That's why it's called L linear MMSE estimation. Okay? Your estimation should be a linear function of your observation. That is called linear MMSE. Okay, so
So the same thing, can you explain little bit about uh, the covariance?
hmm, okay, so covariance. Okay, so I will. Okay, maybe that's this. You mean the R matrices, right?
Yeah, this. Uh,
Hmm. Okay,
yeah,
let's talk
little
about it
about
a
it.
bit. Sure, sure. Let's talk about it a bit now. First the question. Okay, so on covariance matrices. Yeah. I'll solve. I'll just take a couple of minutes and I'll solve problems. The rest of the 1 hour 20 minutes will be on solving problems only. So on covariance matrices, let's see. So basically, if I have a vector x, okay, x1, x2, x3. I am taking an example. It's a random vector x, where x1, x2, x3 are random variables. This is a random variable. This is a random. All these three are random variables, and this is a random vector. Okay. What this covariance matrix is defined as? Assume that. Let assume. Okay, I maybe write down. So covariance matrix CXX is defined as expected value of x minus mu into x minus mu. Actually, it's Hermitian, but I'll take transpose if all the quantities are real numbers. Okay. Now, if mu, that is the mean vector defined as, take the individual mean values of all the random variables. Okay. If all of them are equal to 0. Okay. Then what is the CXX? Same as average of the vector x times x transpose. And this is also called RXX. This is also called the correlation matrix. So covariance means it will have a mean subtraction. Correlation means mean subtraction will not be there. So for a zero mean random vector, covariance matrices and correlation matrix are same. Okay. So now, what if you expand this? What is it? I'll just expand x1, x2, x3 times x1, x2, x3. This is nothing but generally, okay, if I have a Hermitian, let me just go back to the Hermitian. Okay. It'll have a conjugate, conjugate, conjugate. This is same as expected value of x1, x1 conjugate, x1, x2 conjugate, x1, x3 conjugate, x2, x1 conjugate, x2, x2 conjugate, x2, x3 conjugate, x3, x1 conjugate, x3, x2 conjugate, x3, x3 conjugate. Now, if you see these guys, this is nothing but mod of x1 square. This is mod of x2 square. This guy is mod of x3 square. Okay. Now take the expectation inside. So expectation, the whole matrix is same as the individual expectation. This is nothing but mod of x1 square times expected value of x1 into x2 conjugate, and so on. You can fill the other entries. But this is same as the variance, because for a zero mean random variable, the variance is same as the second moment. So this is nothing but sigma square x1. Similarly, second diagonal sigma square x2, sigma square x3. Okay. So now, if I say this particular quantity, okay, take this. Expected value of x1, x2 conjugate is the correlation between x1 and x2. That is, x1 is a random variable, x2 is a random variable. This expected value of x1, x2 conjugate measures the correlation between x1 and x2. That is, by knowing x2, what is the information that I can derive, or what can I tell about x1? Okay. Similarly, if I both these expectation of x1 into x2 conjugate and expectation of x2 into x1 conjugate, both are same except for a conjugation sign. Okay. Both these values are same. This is equal to r means this is equal to r conjugate. But in general, conjugate doesn't, it doesn't affect anything. So you can assume that if you take the mod, for example, both will be going to be same. Okay, so basically, if I take expected value of x1 into x2 conjugate, that means what is the correlation between the two random variables x1 and x2? Is that clear? And like that, you basically in this matrix, every entry will be what is the correlation between different pair of random variables that constitutes a vector x. That's all. And the diagonal elements of the matrix will represent the power, the variance of each of the random variable. I hope it is clear. Is it okay?
Yes.
Okay. So let's now go to problems. Okay, so today we have some interesting, I have selected some 4 to 5 problems. Let's solve it one by one. So
And
this
also, if time permits, we have the solved assignments, I think, for week 7, where we are finding out, I think, inverse, I think, inverse matrix.
Okay.
I think some
Yeah.
2 problems or so. where okay we have X transpose and then X and then X of TS.
Okay, okay.
So such two questions are
Yeah,
there.
we can go over them in the end, actually, if time
Yes, sir.
permits. Or definitely you can point me in the end of the class. Next class we'll start with those questions.
Yes, sir.
Sure. Okay. So question 2. First, I will start with applications, and then each application I'm going to solve, take a problem and solve. Okay. Give some applications of estimating a random signal from a from noisy observations. Okay, that is, I know that there is a desired signal x of t, some desired signal that I want to find out, but I don't know what that signal will look like. It may be random quantity. For example, if you go for a radar problem, in a radar problem, the goal is to find the whether there's a target or not. So the radar transmitter will give a signal. It will go to the target, hit the target, and reflect back. It will reach as a receiver. And depending on the receiver will have some information about the radar target. For example, it will contain the reflection coefficient of the target and so on. But the radar will not know the exact reflection coefficient of the target. So in that case, it will get some desired signal which it wants to estimate, but that desired signal itself is random because the radar coefficient, reflection coefficient is random from the radar's perspective. It doesn't know what the target's coefficient is. So then that is like a random signal. Another example is your ECG waveform, right? You know that your ECG, you have to measure, for example, it should be some peak and troughs here and there, but at any given point in time, it's a random quantity. You don't know what is the value that the ECG will take, right? It oscillates between different peaks. For example, it goes like this, okay? Something like this. So every point, this is across time, this is your amplitude. So see, the amplitude keeps on changing like a random number, like a random, it keeps changing as a function of time. But I want to find what the signal. I want to estimate the signal. All the signals random. Okay, so this is like a estimating a random signal from noisy observation. Meaning, for example, the machine which records the or ECG or EEG will not give the exact ECG. The machine may have some kind of um, you know um, some kind of impairments. For example, it may have some fault, and that basically can be modeled as a noise. So instead of the true EEG, it will give something like this. It will give almost the same, but it may be something offset. Some offset will be there. Okay, so this is like, let's say this is your true ECG, but let's say your red was your observed ECG. So you see, on top of the randomness in the signal, you also have some noise. You get to see on the machine only red color curve, but you actually want to estimate the green curve. Okay, so this is called estimating a random signal from noisy observations. Yeah, in there's a thing on chat. It is greater than threshold. It is target. That's correct. So Mr. Anupam has told radar we estimate correlation between transmit and receive signal. It is greater than the threshold. It is target. That's correct. So in radar there are two types of problems. One is called detection problem. Other is called estimation problem. Detection problem is exactly what you told, meaning that the interest is just to know what is the whether there's a target or not. But more than that, if you want to understand what is this target made of, what are the properties of the target, then that is like an estimation problem. You want to estimate what are the reflection coefficients. You want to estimate what is the angle at which you want to localize the target. You want to know at what distance is this target located. You want to know what is the angle at which this target is located with respect to the transmit and receiver is. Okay. So yeah, you brought in a good aspect of it. In the end, so last class I thought of sharing some research papers and discussing some problems and mathematical linear algebra perspective of it. So I have decided to postpone that till the end of this module, meaning that the last lecture or last TA session of this course, we will go through some radar problems and we will see some estimation of radar parameters using all the tools like music, spirit, and all these things. So we will do that in depth. in the last, so please come till the last class. Okay, but anyways, estimation is also there in radar problem, so you always have this problem of estimating a random signal from noise observations. So first let's see some broad, what is this regime about, then we'll see some application. So basically what I mean by estimating a random signal from noisy observation is your observation x of n can be modeled as d of n plus b of n. For example, n here represents the time index. Okay. N represents a time index. X of n is the observation. And d of n is your desired, albeit it's a random signal. So desired random signal, which we are interested to find. And v of n is the noise. Okay. So what is your goal is to minimize, let E denotes expectation of mod of En square, where En is basically the error between d of n and d hat of n. That is the error between the true dn and the estimated dn. Okay, this error should be as minimum as possible. In particular, I take the mod and square. This mod square is basically for mathematical convenience. You can ask, why not just mod? Okay, why square? Because it so happened that this term x square, mod of x square, has nice properties. For example, mod of x is not even differentiable, but a mod of x square you can always find the derivative. So it so happens that there are a lot of interesting mathematical simplifications that you can do with mod of x square. That's why we define the error as the squared error generally. And there's an expectation because E of n can keep changing with n. So you take the average error across all n. Okay. That is like the expected square error. That's why it's called, this is also called mean square error. Mean because you take the expected operator, square because you take the square of the error, mean square error. Okay. Now, what is the goal? Goal is to find d hat of n, that is the estimator, which minimizes what? What should your estimation goal is? I should be able to estimate d hat of n such that which minimizes, yes, error. Error is what? E. Okay. So basically your block diagram should be something like this. You should have x of n, which is your observation. Okay. And you should pass that through some kind of a system, which is basically estimating what your d is. I would call this as a filter for a want of a better name. Let's say you get observation, pass it to a filter. It will filter out everything else except the desired signal, which is your estimate of your d hat. D. Okay. So, estimate is the output, such that if I have this minus and plus dn, which basically gives en, is as minimum as possible. Okay. The solution basically is that is the optimal filter which does this job of minimizing the error. The optimum filter for this problem is called Wiener filter. Okay. Okay. Side point is FIR Wiener filter. So for those people who have taken some basics of systems course, if I know that it's a filter is characterized by something called an impulse response. And depending on whether the impulse response is infinite duration or finite duration, there's something called finite impulse response filter or an infinite impulse response filter. It's called FIR filter or IIR filter. Okay. So this FIR Wiener filter is equivalent to an LMMSE estimation. Okay, so you can imagine your LMMSE estimation to be something like passing your observation through a Wiener filter. The output of the Wiener filter is basically your LMMSE estimation. We will show how that is the case, and then we are going to use this Wiener filtering property for all the problems that we are going to solve for today. Okay, so now let me tell the application of and the such kind of a problem. Namely that you want to estimate a random signal from a from noisy observations. So first application is filtering. Okay, this is basically the problem above. The problem above. That's all. This itself is another application. Namely that is estimate d of n from x of n equal to d of n plus v of n. That is, given the observation f x of n, you need to be able to estimate d of n. But for what values of n? When x of n is given and d hat of n, that is the estimate of d of n, depends on current and past values of x of n. That is, it should depend the estimate of d of n, that is d hat of n, should be a function of x of n, x of n minus 1, x of n minus 2, and so on till x of 0, or whatever all the history that you have about of x of n for every n. You can make use of all of them and find the estimate d hat of n at the present n. This is called a filtering problem. Okay, or it's also called a causal filter. That is the um, basically that is the estimate. It doesn't depend on the future problem. You because future data, future observations. Because the only fact that such kind of filters cannot be realized. You cannot predict. Tell something about future. Okay, I know future's observation. Now I want to know what is the prediction now or estimation now. That makes no sense. That is not practically impossible. You cannot know what is going to happen tomorrow unless you go tomorrow. You cannot tell what's going to happen tomorrow now. So generally, this filtering problem is what is more practically realizable, and this is called causal filter. Okay, so there is a question on chat. Radar estimate uses Wiener filter. Okay, that's a very good question. I will please remind me this question in the end of this class. The short answer for this question is it's really not necessary. There is more advanced versions of Wiener filters like something called Kalman filters, which basically make use of the fact that okay, I will explain these things in the end of the class, but you can remind me towards the end. But that's a very good question. Okay, causal filter is filtering problem. The next application is called smoothing. Okay, what is smoothing? This application is similar to filtering, but your d hat of n can depend on past, current, and future values of x of n. Okay, it's not always possible to realize, have a smoothing. So where is smoothing application relevant? For example, if I have something like a data like x of, let's say at the first day, the weather prediction was 25 degrees Celsius. Let's say the fifth day weather was 20 degrees Celsius. Okay, these are your observations after fifth day. You are at a sixth day today. This is today. Suppose someone asks you, what is the prediction at second day? What is this weather? Then you need to use the past value 25 degrees Celsius, future value 20 degrees Celsius, everything together. And you would have measured something on the second day also. Put everything together and then find the estimate of the temperature on second day. This is like smoothing. That is, you use both past and present values in order to estimate the current desired signal. That is called smoothing operation. Okay, this is called smoothing operation. The third application is prediction. Here, the desired signal d of n equal to x of n plus 1. That is, you have the observation x of 0, x of 1, and so on till x of n. The desired signal now to estimate is x of n plus 1. Then that is basically called the prediction problem. That is given x of n, x of n minus 1, and so on. What is the estimate of x of n plus 1? This is called a prediction. It's called this kind of a filter. Although it's a Wiener filter, it's more called it's also called as a predictor filter. To be more precise, it's a forward predictor filter because I'm estimating the forward samples. The last is deconvolution. Okay, here generally that if I have x of n is equal to d of n convolution g of n plus v of n. What is deconvolution? Given the convolved values, I need to be able to extract your desired signal. Okay, so here deconvolution in the sense it is not only that I need to estimate d of n, but I also have to deconvolve with g of n, where g of n is also called the known impulse response to the system. Okay, so these are the broad applications of this kind of a problem of asking how to estimate a random signal from noisy observations. Okay, so now we have now stated the problem applications, right? Now let's go into the Wiener filter, little bit about Wiener filter, which is a question 3. Design an FIR Wiener filter, because FIR Wiener filter is what we claim to be the equivalent of LMMSE estimate, right? So that's why let's go to FIR Wiener filter with P weights, because an FIR filter means it has P taps, right? A filter is basically a signal, a tap, it has taps. FIR means finite impulse response. So I'm calling the number of such non-zero taps as P, or weights. I'm calling it as P weights using LMMSE principle. Okay. So what is, let's first write what is a Wiener filter? This is exactly Wiener filter problem, right? Observation you should have, then design a filter such that the output is the estimate of your random noise, random desired signal, such that the difference between that desired signal and this estimate and the desired signal whose error is as minimum as possible, right? So basically, x of n, the observation is the input. Call this as w. Output is d hat of it. Okay, what I do, I'm saying p weights. So collect p observations. That is w is a vector of, what is the dimension of w? I told p tap filter means what is dimension of w? Yeah. So dimension of W is basically a P cross 1 vector. Okay. So I need to collect P observation. That is, I collect x of n, x of n minus 1, x of n minus 2, and so on till x of n minus p minus 1. Why p minus 1? Because I start with n minus 0. Including this, you will get totally p observations. I am collecting p observation. Using all these p observations and the p length weight, that is p dimensional weight vector, I should get d hat of n. This is your p tap FIR Wiener filter. Okay. So what is the d hat of n? Equal to, let's say your w equal to w naught, w1, and so on till wp minus 1. Then your d hat of n is nothing but just the inner product between w and the observation. That is w naught of x of n plus w1 of x of n minus 1, and so on till wp minus 1 of x of n minus p minus 1. Okay. Okay, let me make a small change. I will do conjugation because, just for the mathematical notation. Okay, this same as taking L equal to 0 to p minus 1, WL conjugate x of n minus L. Please let me know if you don't follow. I'm just writing this as a summation. And this is same as the inner product of W and your observation x. If I write x subscript n, that means the first entry starts with x of n minus 1, and so on till x of n minus p minus 1. Similarly, can anyone tell me what does this mean? Just means the first entry starts with n minus 1. That's all. If I write n here, that means the first entry starts with n and then take p values behind it. If it started n minus 1, then I'll take n minus 1 and then take p values behind it. N x of n minus 2. So until x of n minus p. Okay. This is a notation. That's all. Now, what is the LMMSE principle? I told you I define the filtering operation as inner product of W and X. Now I need to design my Wiener filter weights W. But what is the question? Using LMMSE principle. So let's first write the LMMSE principle. Okay, that is, what is this? You need to minimize your error, expected value of your E of n, subject to your d hat of n, that is your estimate, is equal to W Hermitian x, xn to be more precise. Okay. Now let me define the autocorrelation, something like this. Okay. Same as expected value of d of n into x of n. That is same as expected value of d of n into x of n. There's always a conjugation that comes, because if you remember, that's how correlation is defined. D of n into expectation of n minus 1 defined. D of n into x conjugate of n minus p minus 1. We'll just define this vector. Okay. What is the dimension of this vector? It is n p cross 1. Okay. So now let me solve this optimization problem. What is the objective function? Expectation of mod of E of n square. The same as expectation of d of n minus d hat of n. But I have imposed a constraint that d hat of n should be W Hermitian xn, because LMMSE, linear estimation, right? Because the estimation should be a linear function of an observation x of n. That's why this constraint has come. That is your linear MMSE estimation. This I can write it as okay. This I can simplify it as okay. Now let's expand this product. So what is this being? This gives us okay. Is this clear? Can anyone confirm if this is clear? I just expanded into 4 terms. Can anyone confirm if this is clear? Okay, so I assume it's clear. Okay, so now let's see. Now you tell me what is this? This is same as RD of 0. Why? RD of 0 is nothing but expected value of D of n into D conjugate of n only, because it's at 0 time lag, means you should not do any time. So it's a correlation value of D of n with itself. That's why the first term is RD of 0. That is the autocorrelation of the function D with time lag 0, means correlation of the random parameter dn dA of n with itself. That is RD of 0. What is this? This is nothing but R dx Hermitian. No. This is nothing. Okay. This is nothing but W Hermitian. See this guy, right? This is same as R dx. Now this guy here, it is same as, this is nothing but R dx Hermitian times W. Because the W is not random. This is deterministic. So when you take expectation, W will go outside. But now this guy is same as R dx Hermitian. And the last one is W Hermitian into expected value of xn Hermitian into W. This is nothing but RD of 0 minus W Hermitian RDX minus RDX Hermitian W plus W Hermitian W. What is the middle term? Can anyone tell me? Can you identify what is this? Expected value of x of n Hermitian. Can anyone identify what is this? Yes, it's an autocorrelation matrix Rx. Okay, where Rx is equal to expected value of xn Hermitian equal to, what is that? I'm just expanding it again, x of n minus 1 and so on till x of n minus p minus 1 times x conjugate of n, x conjugate of n minus 1 and so on till x conjugate of n minus p minus 1. Okay. Let's multiply this both and take the expected value of every quantity. That is basically your, let's also maybe write it, no problem. Let's write it down. There's nothing but expected value of x of n, x conjugate of n, expected value of x of n, x conjugate of n minus 1, so on till expected value of x of n, x conjugate of n minus p minus 1 Here it's expected value of x of n minus 1 into x conjugate of n. Expected value of x of n minus 1 into x conjugate of n minus 1. So on to like this. Similarly, last term is expected value of x of n minus p minus 1 into x conjugate of n. So on to last is expected value of x of n minus p minus 1 into x conjugate of n minus p minus 1. Okay. Now, what is the first term in the matrix? Rx of 0. What is the second value? Can anyone tell me what is the second value here? Rx of 1. Because I'm computing the correlation between x of n and one, the correlate with the other random variable, which is one time, behind the current random variable Rx of n. Next will be Rx of 2. What will be the last random variable? Rx of, what is the last value? Rx of, can anyone please answer? The last value in the first row. That is correlation between x of n and x of n minus in bracket p minus 1. What is the value? Exactly. So someone told correctly, Rx of p minus 1. Okay. Next row. Now, can anyone guess what is this? Rx of what? X of n minus 1 with x of n. That is, I am comparing with the future sample. This is Rx of minus 1. Okay. This is Rx of minus 1. Because I'm comparing with the future sample. Here, I compared x of n with its x of n, then x of n with x of n minus 1. All the second variables are all past samples. But here, x of n minus 1 is the future sample. So it's Rx of minus 1. Similarly, what is this? This is Rx of 0. What is this? Rx of 1. So until Rx of p minus 2. Next will be Rx of minus 2. What is the last? You can show that Rx of 1 minus p. Like that, Rx of 0. Okay. Okay. Now, if x of n is real, okay, then expected value of x of n times x conjugate of n minus 1 is same as expected value of x of n into x of n minus 1 because this conjugation doesn't affect. Similarly, this is nothing but Rx of 1. Correct? Similarly, Rx of minus 1 equal to expected value of x of n minus 1 into x conjugate of n. This is same as, if it's x is real, then it is same as expectation of x of n minus 1 into x of n. But both are same, right? Because of real quantity. The only quantity which distinguished these numbers are the conjugation here happens for x of n minus 1, but the conjugation happens for x of n here. But if you don't have any conjugation, both are same. What does it mean? Whenever x is a real sequence, then Rx of 1 is same as Rx of minus 1. Or in general, Rx of I, any number is equal to Rx of minus I whenever x is real. Okay, so if you use that property, then this minus 1 will become plus 1. Minus 2 will become plus 2. And what will this Rx become? Rx of 0, Rx of 0, Rx of 0, so on till Rx of 0. Rx of 1, Rx of 1, Rx of 1 till Rx of 1. Again Rx of 1, Rx of 1, Rx of 1, so on till Rx of 1. Correct? And so on till Rx of p, p minus 1, and Rx of p minus 1. This is what is called a Toeplitz matrix. In fact, this is also called a Toeplitz matrix because you see along any diagonal you take, the values are same. Okay. This is also Toeplitz matrix, but in addition, this is Toeplitz plus symmetric. The Toeplitz plus symmetric matrix for a real random sequence or real random signal. The correlation matrix, the Toeplitz and symmetric matrix. But for a general random complex random signal, the correlation matrix is just Toeplitz matrix. I cannot tell that it's a symmetric, but I can tell one thing: it is a Hermitian matrix. See, this is a you can show that. Why Hermitian? Because if you take the conjugation of Rx of -1, you will get back Rx of 1. You can show that. Okay. So, okay, maybe let me write it down. This Toeplitz plus Hermitian. Okay, so let's go back. It was just a small digression. Let's go back. So this was our equation. Let me write down E equal to expected value of E of n square equal to, let's write down, RD of 0 minus W Hermitian RDX minus RDX Hermitian W plus W Hermitian RXW. Now, what is the minimum mean square policy? What is it? What should I do now? Take the gradient with respect to W and equate it to 0. That is our first order differentiate optimization criterion, right? If you want to minimize a function, differentiate with respect to 0 and equate to 0. Differentiate with respect to the variable with which you want to minimize and equate the gradient to be equal to 0 and get the variable. That is what I'm doing here. So let me take the. So you tell me. So now I have told you in the previous class how to take gradients. You tell me what is the gradient of the first term, RD of 0 with respect to W. What is it? Yeah, it is 0. What is the second term? It is same as RDX. Third term, because W doesn't come with a Hermitian. Recollect, I taught you a short trick, right? So W doesn't come with Hermitian. So take the coefficient accompanying it and take its Hermitian. So that is same as RDX. Fourth term is 2RXW. Okay, I solved a question in the previous classes on how to take gradients and Hessians of these kind of functions. So you can refer that and you will land up at this equation. And equate to 0, right? Then what do you get? 2RDX equal to 2RXW or W equal to RX inverse RDX. Correct? This is similar to your LMMSC principle, right? There also you had some R by Y inverse. Here X is your observation. So you have an RX inverse, RXX inverse, for example, times the RDX. So this is also similar to LMMSC. That's why FIR Wiener filter will basically give you an estimate which is same as a LMMSC estimation. Okay, and this equation, very important in the context of Wiener filters. This equation is called Wiener-Hopf equation. Okay, so what is your Wiener filter estimate now? D hat of n is equal to W optimum Hermitian times your observation xn. It is nothing but Hermitian, right? So it's RDX Hermitian, RX inverse X, which is same as your LMMSC estimation. Therefore, FIR Wiener filter, okay, is also known as LMMSC estimation of random signal. Okay, So this was basically to design a Wiener filter using LMMC approach. Finally, let's write down the error. What is the error in the filtering? That is the E min. What is the minimum error? Same as similar to your LMMC error only. Because your estimation same as LMMC estimation. So the error should also be same as the error of your LMMC estimation. RDS 0 minus, I'm just going to write that optimum here. Or dx. This was our error, right? Opt. See, this was our error. See here, this was exactly our error. Now substitute W equal W optimum. Put W equal to this value. R dx Hermitian Rx inverse X. Exit. Put this here. You can simplify and show that your E min equal to RD of 0 minus RDX Hermitian Rx inverse RDX. Okay, fine. So we have reached a good stage now. We will take a 5-minute break, come back and quickly solve very interesting, if time permits, I will solve 3 problems and then we will call off for the day. Okay, so let's take break for about 5 minutes. We'll meet at not 5, maybe 4 minutes. We'll meet at 7:35 again. Okay. Can you see my screen and am I audible? Okay, so today I think not many are responding. Okay, so let me know if there is some problem in understanding or something so that we can go over again. Okay, so let's start. Yeah, is there a question?
No, so the concepts are quite complex, so to understand and assimilate, we need to
Okay.
study more.
Mm, mm, mm. So basically, the idea of maybe overall, if you see, the idea is see, let me maybe at least this particular concept I would like you to understand, namely that I want to predict or estimate a random signal from noisy observation. Is this problem clear first?
We are
Sorry, let's say you have a true ECG. Okay, you have an ECG signal. We don't know, for example, if I know the ECG value at this present time instant, after 2 seconds, I really don't know the value of ECG. So that way, it's a random signal.
okay.
Okay. At the same time, the true ECG may be some signal, but the machine which basically gives me the output will not give me the true ECG because machine may have some fault, some kind of calibration error, and so on. So basically, it will give some slightly, erroneous ECG. That's what I here indicate by green and the red line. The red line is the true ECG. Your green line is the true ECG that the patient you measure from a human being. But the machine may read only red curve as you see here because of the machine's fault. So that fault of the machine you can model it as error.
Okay.
Okay. So this is so what you observe is a red curve. That's called a noisy observation. Why noisy? Because that is not the true observation. That is noise added with the true value added with some noise. So that's called noisy observation. But the actual signal, it's also random signal because you cannot predict at any point. I mean, you cannot say deterministically that at this point this is the value of the signal. That's why it's
Okay.
called random signal. And this particular observation I model is a model as x of n plus d of x of n equal to d of n plus v of n. Okay, where x of n is an observation, that is a red signal.
Okay.
Red is your x of n.
Okay.
Your green is your d of n. The modeling machine fault, which is basically making the green of a green curve to look as red curve, is coming as I'm writing as v of n.
Yes.
Okay, so now if this is the equation, I get to see from the machine only x of n. Then the goal is what is d of n. That is because that's what I want to know. Correct? That is the problem. Is the problem clear now? Hello? Okay. So yeah, there is a question. Noise is to be modeled. Of course, that's true. Noise has to be modeled. Otherwise, I only know that noise has some statistics, but of course, you're true. In general, noise can be modeled as something called Gaussian noise and so on and so forth. Okay, but of course, yeah, that is another part. But this is the equation, math equation. The goal is given x of n. What is the best estimate of d of n? That is the goal. And what I'm saying is, um, pass the x of n through some filter. That will basically filter out all the noise from the observation and give the output as the estimate of dn. Okay, is it clear? And the goal is how to design such a filter. That filter is called a Wiener filter, and the design of such filter is exactly given by this expression. Where is the expression? This expression W is equal to Rxx inverse Rdx, where Rxx is defined as this matrix, that is the autocorrelation of the data in observation, and your Rdx is the autocorrelation between the desired signal and the observed signals x of n. Is the setup clear? Even if you didn't follow, or maybe even if the rest of the things derivations was difficult, is a high level setup clear? You're given some observation, noisy observation of random signal. Goal is to pass that observation through a filter and get estimate of the desired signal. And the filter which you have to design should follow this particular equation as I show here. Is the high level idea clear? Yeah, I think someone was asking me. Okay, so maybe at least one of you can confirm if it's clear. Can one of you confirm? I think I see Mr. Anupam answering very attentively in the session. So, can anyone else confirm if it's clear? Okay, so I hope it's clear. Let's move on. Okay, let's move on because we have only 20 more minutes. Let's see how much we can do. Okay, okay. This is the next problem. Let T of n be AR1 process with. Okay, what is AR1 process? D of n can be modeled as some c times d of n minus 1 plus the other fraction 1 minus under root c square times some v of n, or w of n where is some noise. That is auto-regressive process. I think professor would have mentioned about auto-regression, right? This is called auto-regressive process. That is, the value of the signal at the present instant is a sum of the value at the previous instance plus some noise. It's a weighted sum where c and under root of 1 minus c square. Such kind of process of d of n is called a auto-regressive process. What is the meaning of one? Means it depends only on the previous sample, not on any other sample. If it were AR of 2 process, we'll have something like this. D of n is equal to C1 of D of n minus 1 plus C2 of D of n minus 2 plus some C3 of W of n. This is called an AR2 process. That is, it depends on two previous samples. Okay, so this is called the AR1 process. Okay, so I'm saying that D of n, that is a desired signal, comes from an AR1 process. It's an auto-regressive process with autocorrelation sequence Rd of k equal to alpha power modulus of k, where alpha is some number between 0 and 1. Now let d of n be observed in the presence of uncorrelated white noise V of n with variance sigma square V as x of n equals to d of n plus V of n. Okay, that is, you observe the desired signal as x of n from a noise, which this noise is uncorrelated with d of n and is a white noise. That is, expected value of v of k into v of j equal to 0 as long as k is not equal to j. That is the meaning of white. Okay, that is, among the noise samples with different time lags, the correlation is 0. That is, you cannot tell the noise sample at some other time if I know the noise at this point. That is called white noise. Uncorrelatedness that I show here means expected value of d of n, d of k into v of j equal to 0 for all k comma j, even equal to k, k equal to j, or k not equal to j. That is, you cannot tell anything about the desired signal if you know the value of noise and vice versa. That is the meaning of uncorrelated white noise. Okay, so what I told is this, the desired signal forms an auto-regressive process AR1. That is, it follows this particular relation, and you get to observe the desired signal via noisy observation x of n. Okay, what is the question? Question is, design a first order LMMSC filter or Wiener filter to estimate D of n. That's all. Okay, answer. So first order means it will have two inputs. First order filter means it has two weights. That is, weight for the present sample and weight for the previous sample. First order means just one sample before. Two weights, W0 and W1. That is, the weight filter is, it takes current sample and just the first order previous sample. Pass it to your filter W0 and W1 and obtain T hat of n for every n. So what is your W opt? Can anyone tell me what is the optimal W? Just Rx inverse of Rdx, right? That was what we derived in the previous solution. So now the rest of the problem is to compute these two work values. That's all. So first, let's do computation of Rx. Now, what is that Rx? So here your observation xn is equal to just it's a two vector xn and xn minus 1. Therefore, Rx equal to expected value of xn Hermitian, which is same as Rxx of 0, Rxx of 1, Rxx of 1, Rxx of 0. Now tell me what is Rxx of 0? Okay, let me maybe write down a little more because it's not clear. That is expected value of, okay, let me write down this. Rx of 0, okay, nothing but expected value of x of n into x conjugate of n. That is same as expected value of d of n plus v of n into d of n plus v of n, the whole conjugate. The same as expected value of, I can just write three terms will come, square with expected value of d of n, v of n conjugate plus expected value of v of n, d of n conjugate plus expected value of mod of vn square. What is the first value? Rd of 0. What is the second value? Can anyone tell me? Please tell me what is second value? See, given the problem is what? V of k, V of j, their correlation is always 0. So what is this? It is 0. Okay. Similarly, third is also 0. And fourth is what? Please tell me what is fourth? The variance of noise. What is the variance of noise? So plus sigma square b. Add all of them. What is Rd of 0? You have given the question, it says what is Rd of k is equal to alpha power mod k. What is Rd of 0? Alpha power 0, which is 1. Therefore, Rx of 0 is equal to 1 plus sigma square v. Now, what is Rx of 1? Because the matrix has Rx of 0 and Rx of 1, right? And Rx of 1 and Rx of 0. So I need you to compute Rx of 1 also. Rx of 1 is what? Expectation of x of n into x conjugate of n minus 1. Same as expectation of, I'm just writing the final result, d of n square plus expectation of v of n into d conjugate of n minus 1 plus expectation of d of n into v conjugate of n minus 1 plus expectation of v of n into v conjugate of n minus 1. Now this guy is Rd of 0. This is equal to 0. This is equal to 0. What is this? This is also 0. Why? Because I told the noise samples are uncorrelated with any other instant. See, here I'm saying V of n into V of n minus 1 at two different time instants. So their noise samples will be uncorrelated. So the correlation is 0. So this is same as Rd of 0, which is same as alpha power. Sorry, not Rd of 0, right? This is Rd of 1. Same as alpha. Because alpha power 1 is alpha. So what is your Rx? This is your Rx. Rx of 0, Rx of 1, Rx of 1, Rx of 0. So Rx of 0 is what? 1 plus sigma square V. Rx of 1 is what? Alpha. So it's just 1 plus sigma square V alpha alpha 1 plus sigma square V. Okay. So we found what Rx is. Now we'll find Rdx. Nothing but expected value of d of n into x conjugate of n minus k for some k. But here we only want to find with respect to k equal to 0 and 1. For k equal to 0, expected value of d of n into x conjugate of n is equal to expected value of d of n into d conjugate of n plus b conjugate of n. What is this value? Can anyone tell me? This guy will go to 0 because noise and desired signal are uncorrelated. This is same as Rd of 0, which is same as 1 because alpha power 0 is 1. This is equal to 1. For k equal to 1 now. That is expectation of d of n into x conjugate of n minus 1. Can show that this is Rd of 1 plus 0, which is alpha. Therefore, your Rdx equal to Rd 1 comma 1 and alpha. Okay. So then what is your weight? W optimum equal to Rx inverse Rdx, which is same as inverse of 1 plus sigma square V alpha 1 plus sigma square V, the whole inverse times 1 alpha. Just solve this. You can show that this will just take the inverse of this matrix, multiply it with the vector. You can show that this comes out to be 1 plus sigma square V, the whole square, minus alpha square times 1 plus sigma square V minus alpha square times alpha into sigma square V. So you should design your filter, your Wiener filter, with these weights so that the output is the LMMSE estimate of the desired random signal D of t. Okay. If you have any question, please ask me now. Okay. Let's now move to the next problem. Okay, this is problem 5, right? This is problem 4. Okay, this is problem 4. This is 3. Yeah, 3. Okay, so the fifth problem, design an optimal first order linear predictor for an AR1 process X of n that has an autocorrelation sequence given by Rx of k equal to alpha power mod k. Okay, so you understood. So basically the given is you have all the current till the current sample, you have the observations. You need to predict what is the next sample using a Wiener filter. That is optimal first order linear predictor, means Wiener filter first order. So just using the present and the past sample, what is the next sample, the future sample. And I know that this samples, all these data samples follows an AR1 process. That is something similar to this. Where is it? AR1 means your x of n will be equal to c times x of n minus 1 plus under root 1 minus c square times your some noise. This noise will keep independently generated at every time. This is it is the first the x of n depends only on x of n minus 1. That is called AR1 process. For such kind of process, what is the optimal first order linear predictor? Okay, we will solve this question. Okay. So your x hat of n plus 1, which is a predictor, should be, since it's first order, it will have only, it is of the form w naught xn plus w1 xn minus 1. Okay, only one order previous instead you should go. Again, what is it? You need to just compute w. What is the w optimal? If you have w is equal to w naught and w1, w optimal is given by, again same thing, rx inverse of rdx. Same thing. The only difference in these questions is how to compute these two quantities, rx inverse times rdx. Okay. Now, what is your x here? Observation x of n and x of n minus 1. Now, please tell me what is the desired signal d of n? That is, what am I interested in estimating in this problem? What is the desired signal that I'm interested in estimating?
X itself, sir.
The desired, I want to estimate x of n plus 1, correct?
Yeah.
Because I need to predict what is the next value. Is that correct? That means the desired signal which I want to estimate is x of n plus 1. Is it correct? Okay. That's all. So we have identified an observation and our desired signal, right? Now, what is our R of x? That is R of x, the correlation of the observation. Expected value of xn Hermitian, which is same as expectation of, I mean, you can show that this is nothing but Rd of Rx of 0, Rx of 1, Rx of 1, Rx of 0. But I given the question Rx of k is equal to alpha power mod k. So what is Rx of 0? Alpha power 0. What is alpha power 0? Yes, please. What is, yeah, okay. So Rx of 0 is 1. What is Rx of 1? Put k equal to 1. Alpha power 1 is 1. Alpha. So this is alpha, this is 1. So we have found Rxx. Now Rdx is equal to expectation of d of n into two values, x conjugate of n and d of n into x conjugate of n minus 1. The same as expectation of x of n plus 1 into x conjugate of n and x of n plus 1 into x conjugate of n minus 1. Now what is this? Rx of 1. This is what is Rx of, what is this? I'm taking the correlation between x of n plus 1 and x conjugate of n minus 1. So it is Rx of 2. What is Rx of 1? You see here. Rx of 1 is at k equal to 1. Alpha power mod 1, which is same as alpha itself. What is Rx of 2? Alpha power mod of 2, which is alpha square. So I know what Rxx is, I know what Rdx is. Therefore, W opt equal to Rxx inverse Rdx. You know both the values, substituted here. Take the inverse. can show that W opt is given by alpha 0. 0. See, that means your x hat of n plus 1 equal to alpha times x of n. See, although I wanted it to be a function of xn minus 1, the weight for xn minus 1 became 0. Can anyone try to tell why is this happening? Yes, can anyone try to tell? Why is your, I wanted x hat of n plus 1 to be a function of x of n and x of n minus 1. But I landed up such that the optimal weight has 0 for x of n minus 1. Why? That is, what this equation says is x hat of n plus 1 can only be a function of x of n, not x of n minus 1. Why is that the case? See, the result, this is because the original function follows an AR1 process. By definition, AR1 process, you can have the present sample can depend only on the just past sample. It cannot depend on any other past sample. And that is what this optimal filtering is also telling us. The sample at n plus 1th time instant can only depend on x of n. It cannot depend on any other past sample. That is your AR1 process. That's why your weight for your x of n minus 1 has turned out to be 0. Okay. Okay, we'll just stop with error computation alone. With that, we'll stop for today. Now, what is the MMSC in prediction? What is the MMSC? That is, what is the error in prediction? Just use the formula. E min equal to Rx of 0 minus W naught Rx of 1 minus W1 Rx of 2. But W1 is anyway 0, so this goes off. This is same as 1 minus alpha square. Because W1 is alpha, Rx of 1 is also alpha, equal to 1 minus alpha square. What does it tell you? It tells as alpha increases, E min decreases. Why is this the case? Let me go to the extreme case. If alpha equal to 1, what does it tell? E min is what? 0. Why is this the case? This is because if alpha equal to 1, what is your Rx of k? Equal to 1 power mod k equal to 1. That is, if I tell you the present time value, almost surely, deterministically, you can tell that at the next time what is the value. Namely, that the value assumed at this point will be able to exactly 100% surely will tell you what is the value in the next time instant. If you can 100% tell with almost surety, then there is no error, right? There is no error because alpha basically, where does alpha come from? It is coming from autocorrelation function, and the meaning of autocorrelation is with what percentage can you tell about one random variable when you know the knowledge of another random variable. So if alpha equal to 100% surety, with 100% surety, I can tell the knowledge of the next time's instant when I know the current time's value. That's why when alpha equal to 1, E min goes to 0. Okay, and similarly, if alpha is not equal to 0 or equal to 0, the other extreme, if alpha equal to 0, what is the meaning? E min is equal to 1, maximum error. Why? If alpha equal to 0, the autocorrelation becomes 0 power k equal to 0. That is, knowing the current time, the data value in the current time instant is not at all useful. It is useless in terms of predicting the next time instance value. That is basically your alpha equal to 0 case, and in that case, the error that you will land up in estimating the next time instant is always going to be maximum, namely 1. Okay. Therefore, correlation is the heart of estimation theory. Is at the heart of estimation theory. Okay, so it's already 8:05, so we'll stop with this question for today. Um, yeah, so there is a radar estimation. One person asked about it. Okay, so is Wiener filter used in radar estimation? The answer is more complicated filters are used, because if you, for example, see this W opt, it is independent of the data values at now present, right? It only depends on alpha, sigma square, only these two values, which are constant across time. It really doesn't change. But what will happen if sigma square V itself changes and you don't know? That is, noise statistics keep changing, which is the real time environment. You may have clutter at this point in time, you may not have in some other point in time. Similarly, your alpha can keep changing, your correlation sequence value can keep on changing. Then what is that? That leads to something called adaptive systems. You need to adapt your system. See, this W opt is something fixed. It is independent of your data at any, it's independent of n, for example. But in adaptive system, that is no longer the case. At every instant, you'll keep on changing your weight. And that is the kind of systems you need to, kind of algorithms you need to think about radar systems. You need to adapt. So there's a branch of signal processing called adaptive signal processing, and you need to go to that particular section and then derive solutions from there. So for real-time applications, it's not just sufficient to do Wiener filtering. Wiener filtering is something called stationary process. That is, your characteristics of every other signal doesn't change with time. But in reality, the characteristics of noise, characteristics of this data, everything will keep changing with time. In which case, there's something called adaptive signal processing. Means you need to build your systems such that they're adaptive in nature. Okay? For example, one point reference that I can point to you is something called Kalman filter. Kalman filter is precisely used for radar object tracking. If the radar object moves, the target moves, then all the characteristics of the system changes. Then you need to adapt your weight. Kalman filter is designed for one of the techniques that is used behind radar tracking. You can maybe they are little more advanced signal processing topics, which are little beyond the scope of this course. So, but you can always go and refer to these references if you want. Okay, so that basically brings me to the end of today's session. If you have any questions, I can answer. Otherwise, we can call off for today.